Hey January, this is Piter Pasma, and today I'm going to explain about SDFs. First, I will explain what an SDF is. So SDF stands for signed distance function, and what that means will become clear later and doesn't really matter. What matters is that it's a mathematical function that you can use or that defines a shape. It can be a two-dimensional or three-dimensional shape, even more dimensional, but we're definitely not going to go there. These functions, they're actually not very complicated, and there's a good possibility that you have actually been using SDFs in some form or another in your project so far. And what I hope that you would take away from this video is that you will recognize when you are using functions that are like SDFs and can somehow mangle your program into that actually being an SDF, because that will allow you a very great tool set of stuff that you can do with SDFs. And I will show a bunch of things that you can do with SDFs and show what they are, and hopefully also how to recognize them in your own projects. So here we go. I'm going to do this in P5.js web editor, just to make it really simple, accessible for all. I'm not going to use shaders today, and I'm going to I'm also going to keep it to two-dimensional SDFs. We're not going to do 3D stuff today. So I will start by defining a random function that I like. This is partly because P5.js is slow and it's the one I'm used to. We'll use a bit bigger canvas. I'm just going to write a little bit of code. We're gonna start with a nice background color. We're going to need a function to draw a circle, because I don't like the one P5 has. So the first thing is that it's going to take a coordinate, and coordinates are like two numbers. So in this program, I'm going to use like arrays of two elements to represent coordinates, which I'm doing here. I'm passing an array as a parameter, and it's being automatically split into the two parameters x and y. This is JavaScript. I hope that's a little bit familiar. So the circle also got a radius and a color, and we're going to draw them without stroke, fill them with the color. Then we're going to use P5 circle function, except that we're going to let our coordinates, I just like this, I'm going to make the coordinates go from -1 to +1, because, and then stretch over the screen, even though it's 800 pixels. So I'm going to do the scaling right here. So first we add 1, and then we multiply by half of the width. And we do the same for y. We add 1, and we multiply by half of the width, so that the aspect ratio also stays right. And then the radius, and we have to halve the radius here because the P5 expects a diameter, which is why I don't like the circle function. So I'm gonna define one more other function, or one that I like, which is the L. L stands for length, and it's going to calculate the length of a vector. So that's like this formula. It's like Pythagoras or Euclid from Elements by Euclid. 300 BC, so gotta cite your sources. And then there is the so we have this function. Now we're going to define the SDF. So an SDF is very simply, it's a function that is defined for everywhere in the space. So it gets a coordinate as the input parameter, and what it returns is simply. So this is about the shape. So the shape has an inside and an outside, and on the outside of the shape, the function is positive, and it represents like the distance to the surface of the shape. And on the inside of the shape, it is negative, and it also represents the distance to the surface of the shape, but negative. And that still might sound complicated, but we're just going to write one, and we're going to make a circle. A circle is one of the simplest SDFs, and you can probably figure it out, but it's like the length of the vector minus the radius of the circle, which is, let's say, 0.3, because we are from -1 to +1. So just imagine this function. It is like at exactly 0.3 distance from the origin, it is 0, because we're subtracting 0.3. And at that distance, that's exactly one circle. And on the outside, it is larger than 0. On the inside, it's smaller than 0. This is perfect. It's a SDF. So now we're going to visualize it. So to do that, we're going to not clear the screen every frame, and we're going to draw 1,000 points every frame. And we start with a random point. So that is R2 minus 1, R2 minus 1. It's a random point between -1 and 1. Then we ask the SDF, what is the SDF? D is the SDF of P. Then we're going to determine the color, which is by default, it's black. And if D is smaller than -0.01, we will change the color to blue. And if it is larger than +0.01, we will change it to orange. And then we simply draw the circle, and with P and a radius of what was it? It is that's still in regular pixels, right? So we're just going to say 2 or something, and the color, which is this. And if I didn't make any errors, we should get, okay, so this is a circle. I hope that so far this all made a little bit of sense. We're just drawing random points everywhere in the screen, and depending on whether this function returns a positive, a negative, or a number close to 0, we change the color of the point, and we get a circle. It works very well. That's nice. Now we have a circle. We will, SDFs are all about functions. So what we're going to do is we're going to define a function for a circle and an SDF for the circle that takes as the input parameter, of course, the coordinate. We are also going to give it like a center coordinate, so we can move it somewhere, and of course a radius. And in order to move it to the center coordinate of the circle, as you can see, the circle is now centered around the origin. It's simply a question of we subtract the center coordinate from the actual coordinates of P that are being asked. And it's kind of weird that you have to subtract them to translate them the other way, but you have to sort of wrap your head around it. The SDFs do things just the opposite way sometimes, and otherwise you just try it both times. So now we just return the length of x, y minus the radius, and we're going to check if this works. SDF circle of x, y, and with center, well, starting 0, 0, that's where it was, and a radius of 0.4, slightly bigger. Yeah, that's a circle. And can we move it? Yeah, we moved it down and to the right, so that's fun. We can actually put this in a variable, and we can like make another shape. It's a line, and it's a very simple line. What's the SDF of a line? Well, a horizontal line looks like this. It's the y coordinate. We can see here, if we return this line, we get a beautiful like shape, except it's yeah, right, the shape was blue, right? We are yeah, we have to turn it around, so we want the blue at the bottom, so we have minus y. And now doing a minus on a SDF basically inverts the shape. It makes the orange blue and blue orange. And to move it, I want to move it down a little bit, so it becomes like it's like a horizon. Yeah, and now it would be like kind of nice if we can also put the circle back in the scene. So how do we combine shapes using SDFs? And like I said, these are functions that they want a minimum distance to the closest shape. So we just take the minimum of the ball and the line, and that works. Now we have both shapes, and I'm actually going to type math.min, which is the built-in browser minimum function, because it is incredibly much faster than the P5 version of min, like more than 4 times. So yeah, it's worth typing math dot sometimes, or you know, writing your stuff in vanilla JS. So as we're seeing, the shape here, they're actually like not drawn on top of each other, because you don't see like the bottom part of the circle, but they're actually the union of those two shapes. Now, that's pretty cool, but why? What's this for? Well, we're gonna do a few other things with the SDFs. Instead of the minimum, we can also take the maximum. And if we take the maximum, what we get is the intersection of both shapes. So we get the part where both shapes exist. So that will be this lower part of the circle intersected with the plane. And as you see, this works. So yeah. What else can we do? We can, by inverting the ball, we can also subtract the ball from the plane. Yeah, and yeah, let me see what else. I think I'm going to yeah, so we're going to I'm going to show a few other tricks that you can do with SDFs. We'll turn this back into the minimum. I'm going to remove this math, by the way. For this program, it doesn't really matter that much. And if we make if we have like well, I'm gonna show some more tricks. Yeah, so we go back to the line. what we can do is, or no, we're going to the ball. Here we are, the union of both. And so there's a funny thing we can do, and we can take the absolute of a distance function. And what happens then, so we do ball is the absolute of ball. What happens then is that the distance function becomes positive on both sides, which means that it doesn't really have an inside anymore, but it's still 0 at the border. So if we look at it, we just see the line of the circle. However, we can, I didn't show that yet, but we can do something else with SDFs, and that is called to inflate them. If you subtract a number from an SDF, it gets bigger. The shape gets bigger because it makes sense, because you stay on the outside of the shape. The distance function gets smaller every year. That means the shape got closer from all sides at once, so it inflates. And if you do that to the just a circular line, you will get the inflated circular line, which is like the circular disc, or well, this shape. And this is what we call for SDFs the onion operator, because it creates like where there was originally, if we don't do this, we have just the ball, and it creates like a line and a shell where the ball was. And we can, in fact, like onions, we can repeat it into layers, and we have just to make the shells a little bit smaller every time. But if we do that, now we have double lines, and we're still like, doing stuff with SDFs. So what is the use of this? Let's say, I hope I'm sparking some ideas by now for people doing stuff with generative programs. But see, let's say, I want to continue still into the box function. I haven't shown a box yet. So what I'm going to do is I'm going to remove this. We're going back to the line. That's this one, and I'm going to just put it in the middle of the screen, and I'm going to take the absolute of it and subtract a little number. And as expected, we get a band, a horizontal band, and we make another one, call it lin2, for the x coordinate. And what do you know, it's a vertical band. What do we get if we take the intersection of these two lines? We get a square. So we made a square. However, this square isn't really the coolest square that you can get, because if we try to inflate it, let's subtract a little, it just gets bigger. But what we would expect is that the corners also get round, because it inflates, and it's about the distance to the corner of the cube. So instead of this maximum function, I use a function that I call the edge function, and I usually call it k, and it looks like this. I'm just typing this from my cheat sheet. There we go. What's this? What's this? You may wonder. So let's show what this distance function look like, the k of x and y. And it's just this. It's an edge. But what is an edge? An edge is the same thing as like if you have the x thing and you intersect it with the y thing. So the maximum of x and y, that's also an edge. But the difference is that if I inflate this one, it's pointy. But if I inflate the K version of this, it's nice and rounded. So if we use this also to make our box, so minus 0.3, absolute minus 0.3, and it's slightly less round, we get a nice rounded box. And well, that's what I wanted to show. Because let's say that you're writing your generative program and you want a margin on your page. You don't want to go all the way to the edge, so you got this if statement, and you probably have like if your coordinates are going from -1 to +1, maybe you figured out that you can simplify it by doing the absolute of x less than 1/8, less than 0.8, absolute of y less than 0.8, and then you draw stuff. This now you have a margin. So if we look at this if statement, we can sort of rewrite it. Like we can take the 0.8 to the left side, minus 0.8 here, minus 0.8 there. There we go. Oops. And yeah, what else can we do? Well, we see here we have two comparisons with smaller than 0, and if both of these have to be smaller than 0, we can also like take the maximum of them, you know, and check if the maximum is smaller than 0, because if the maximum is smaller than 0, then they both have to be smaller than 0. Oh wait, I also need to remove this bit. Yeah. So now when we look at this, this looks a lot like a distance function. And what we can do now, if we have like, let me comment this and put it back here. If we have our instead of the maximum here, we can also use our nice edge function, and we can use this distance function, and instead of having a boring square margin with pointy corners, you're going to have a very cool and fresh, totally not retro, rounded square. And yeah, this is one of the things of SDFs. Like, you may have formulas like this in your program, and you can, yeah, you can search them. So you can try to do weird stuff. You can now make other shapes than squares. I wanted to explain about the repetition operator. I also wanted to explain about how you can mirror things using the absolute function. It has multiple uses. But I think this video has gotten long enough, so I'm going to go through a couple of quick references right now. I have one reference, that's Inigo Quiles, and his articles are amazing, and especially these two. This is a list of 3D SDFs and 2D SDFs, and I'm going to look at the 2D SDFs. So we see our circle here, that's the length of P minus R. The only problem with all these little bits of code is that they're written in GLSL, and that's not JavaScript. So you're going to have to figure that out. The awesome part about it is that he also has YouTube videos where he explains how he derives the formulas, and that's highly recommended. So yeah, you can do that. It has some here a little bit about the onion operator. The 3D SDFs are also kind of neat to check out, not because of all these shapes, because it's a lot of shapes, but there's a few more operators here that also work on 2D SDFs. You just need to try them out, and they will change your SDF. And yeah, they work magic. I am actually just going to show you the repetition operator because why not? You can click away if you think you got the point now. So let's return to well, first let's write a box function because we deserve a box. It's x and y. We need width and the height, and oh yeah, and the centers point where it goes, and then we do pretty much the same, except instead of the we do the k here of the absolute of these values, or did we do the absolute first? No, we do this, yeah, and then we subtract the r inside the k. So that's a box. Now we're going, we can replace that here. It's a SDF box of x, y. Where do we want it? We want it at 0.00. Let's just put it there. And the width and the height. Oh, I did that wrong. This the R, W, and H, and then this is this box will be 0.2 by 0.2, and that's it. We should get a box. We do. All right. Now let's repeat this box. We have to repeat. I have to. Is this still in Desmos here? No. Sorry. That's. How do I explain this? So if you if you subtract the floor rounds value down, right? And we're gonna do math of floor because it's way faster. And so it rounds down. If you subtract it, you get like this sawtooth shape function that goes from 0 to 1 and then back to 0 to 1, back to 0, and it's all these nice diagonal ramps. And we want these ramps to like happen at intervals of r. So we divide x by r. And to compensate for that, at the end we multiply by r. What we're also going to do is we're going to subtract 0.5 more. This makes the sawtooth go from minus 0.5 to plus 0.5. And this keeps like a repeating shape of lines that cross the origin. And that's important because as you can see here, this square, it goes through the origin. And if we now want to repeat it in the y direction, we can do SDF repeat of the y coordinate. And let's say we want to repeat it every 0.4 units. Then this should just work. No, why doesn't it work? Oh boy. Oh, we should return x. And then, it works. Except that our squares are slightly too big, so it's not looking as nice. There we see a whole bunch of repeated squares. So that's the repetition operator, and it's extremely powerful because you get all this stuff basically for free, and you can repeat the x coordinate, and you get that. So mirroring with the absolute function, well, I'm just gonna demonstrate it shortly, but I'm not gonna talk about it too much. You can just try it out for yourself. But now there's two cubes or boxes, I mean. So another fun thing is if we change this back to the, what is it, the circle, yeah. In X, Y, and this is just a single radius of, say, 0.2. We get, yeah, now we have two circles. We can also put this in a variable again. And I think if we make it, then we can have the ball. We can repeat the ball every say 0.4 things, and let's see, does this actually work? I don't think this will work. Whoa, this is not this is a different error. What's the type? Destructured something. Oh wait, we shouldn't. SDF ball is SDF rep. Yeah, oops. Good thing it errored, because I might have gone into infinite recursion. Yeah, so we get kind of like a repeated ball, except it's not entirely proper. However, if we instead take the absolute of this ball, we get a bunch of lines, and we can inflate those a little. And now we see that we have like this. Did I do this right? Let me check my. Oh, this particular formula is not in my cheat. I will move them a little bit closer together and also make them thinner, like maybe that. Yeah, this is pretty cool, right? If I put the, I will put this function here and put it all on one line like that, because we are going to make a second ball, and we call it bubble. And so we're going to be moving the one ball a little bit to the left and the other ball a little bit to the right and left the other way around. Anyway, so yeah, so this one's left and the BBL is right. So yeah, now what shall we do? Let's intersect them. And yeah, I think that's pretty cool. I forget how it looks slightly different than the first one I did. Maybe it was 0.1 there. Well, you can try out some stuff yourself, but I think this should sufficiently demonstrate the power of SDFs. I really hope you find some ways of like incorporating them in your programs and recognize where they already exist. Like when are you like checking the distance to a circle sometimes? Can you do it with another shape? Or are you like checking for the intersection with a really big square or small square? Do you want something else? SDFs make all of this possible. So I really hope that you enjoy the video, and please like the video, and if you want you can subscribe, but I get a lot of notifications, so don't worry about it.